Morning student. In the lecture series of linear algebra, we are going to start a new concept of vector subspace. Is the part of vector subspace. So we are going to start the direct sum of subspaces. The objective of this lecture to students know about the linear combination of vector, linear dependent and independent vector, and to understand the properties of linear combination. So we will continue with the linear combination, and first we will try to understand the linear sum of vector spaces and subspaces. So let's move to the lecture. Let's move. Become direct sum and linear sum. Now we're going to start direct sum of linear sum of vector space. So just move. Linear sum of vector space. Oh, so linear sum or direct sum is the let Qf, where F is the field and Wf are to vector space. Are to vector space. Then of here. Then the linear sum
सर आवाज सुनाई नहीं दे रहा है.
the linear sum can be defined as u plus w is equal to u plus w at q belongs to v u and w belongs to. Now we take a theorem to show this theorem. If uf and wf are two subspace of vector space where then u plus w f is also a subspace. Proof: If U and W are two subspace of vector space Vf, then U plus W is also a subspace of Vf. We will prove it. Now linear sum, linear sum, this is the linear sum of, this is, this is linear sum U plus W is not equal to 5, because this is the linear sum, so one element is always exists here. 0 belongs to U and 0 belongs to W. This is U. So 0 belongs to U plus. Now if X, Y belongs to U plus W, then X is equal to, in the form of U1 plus W1, we can take X is equal to form of U1 plus W1, and Y is equal to taken U2 plus W, because the element of U plus W is the come from U, U1 and W1. So we can write U1 plus W1 form, where U1 and U2 belongs to U and W1, W2 belongs to, and alpha, beta belongs to X. These are the scale. These are the scale. So we will show that alpha X plus beta Y belongs to U plus, because we know a sub, if W is a subspace of Vf, if alpha X plus beta Y belongs to U plus W, where X and Y are the element of W. So we put the value alpha X plus beta Y, and we put the value of X U1 plus W1 plus beta U2 plus W. We can say alpha U1 plus alpha W1 plus beta U2 plus beta W. That means we can say alpha U1 plus beta U2 plus alpha W1 plus beta, because this is the element of U and this is the element of W. So we can say, given UF and WF are vector subspace. So alpha beta belongs to X, X, Y belongs to U. That means alpha X plus beta Y belongs to. Similarly, alpha beta belongs to X and XY belongs to W. Then alpha X plus beta Y belongs to. because because U and W are two subspaces. These are already subspaces. So U alpha U1 plus beta U1. So so we can say that alpha U1 plus beta U2 belongs to U. Alpha W1 plus beta W2 belongs to U. That means that means we can write alpha x plus beta y belongs to W plus. So U plus W is the subspace of. So U plus W is also subspace of. Again, I repeat the theorem. You can understand easily. Given that U F and W F are two subspaces of vector space Vf, then we have to show that U plus W is also a subspace of F of V. For this, we have to show that alpha x plus beta y belongs to U plus W because this is the linear sum. So U plus W is always some element, have some element, not be empty. So U belongs to V, 0 belongs to U, and 0 belongs to W. So 0 is always element of U plus W because U and W are subspace, and 0 is element must be in subspace. So we can say that 0 is the element of U plus W. Now we will find out. Now Now we will find out the way how to show that this is a surface. For this, we take alpha and beta from field F and x and y from U plus W. U plus W. So x1 we take x is equal to U1 plus W1 and y is equal to U2 plus W2. We put the value x and y alpha x plus beta. Okay. So by this we get alpha U1 plus beta U2 and alpha W1 plus beta W2. This is the belongs to W and this belongs from U. So this will when we write that alpha x plus beta y belongs to U plus W, and this is the condition for a surface. So this is easy and important theorem. Now we move direct sum of direct sum of sum of subspace. A vector space where A vector space where is called the direct sum of its surface and WF if each element of VF each element of VF we can present in the form of each element of VF can be VF can be represent represent in the direct sum of U and VF is equal to UF plus. If we can write each element of VF in the form of UF plus WF, then we can say that these are the direct sum of U and W. For direct sum, now I write a definition of disjoint. Disjoint subset. If two vector subspace of VF, then U and W we can say disjoint if U intersection W is U. If no element are common in U and W, then we can say these are the disjoint surface. Now we write a theorem. A necessary and sufficient condition for a vector space to be direct sum. A necessary, very important theorem. Theorem statement we can choose. The necessary and sufficient condition for a vector space for a vector space to be the direct sum of two of its surface UF and WF are. First A, V is equal to U plus W, B U intersection W. These are the two sufficient and necessary conditions that we have to be the sum of two vector space U and W. Then V is equal to can be write as U plus W and the U intersection W is 0. Now the proof is necessary condition. Necessary condition. What is the necessary condition? We assume that we assume that VF is direct sum of its surface. Then by definition each element of V belongs to V can be written as in the form of a direct sum of U belongs to U and W belongs to W. So V is equal to U plus number one equation. We can write. So one is satisfied. Now for B, now for second condition, we take U intersection W is not equal to 1. So there exists an element. So now there exists a common element. So we take X belongs to U intersection W. That means X belongs to U or X belongs to W. That means X is equal to can be write as X plus 0 where X belongs to U and 0 belongs to W. Because this is from V and X is equal to 0 plus X where 0 from and X belongs to Now it concludes that now it concludes a non-zero element of x belongs to V can be written as can be written as a direct sum of subspaces U and V which each contradict with our assumption conjunction that this is not a direct sum. This is not for only zero. So only zero is the vector which is common, which is common in U and now this is proof that zero is the common element for U and V if it can be written as direct sum of V can be written as the direct sum of U and W. Now sufficient condition. Now sufficient condition let V is equal to U plus W and U intersection W is, then we will show that we will show so that V is equal to any element of V can be as a direct sum of W. Now by condition by condition that by condition if we say that V is any element can be written as direct sum of U plus W. So we take if possible, it is not unique. Not unique. Because the sum of that sum is unique. V1 can be V can be written as a unique form U plus W. but we say that this is not unique. So we take u1 u. So we take so we take v is equal to u1 plus w1 form where u1 belongs to u and w1 belongs to u2 plus w2 where u2 belongs to u and w2 belongs by comparing both by comparing both u1 plus w1 is equal to u2 plus, so we can say u1 minus u2 is equal to w2 minus belongs to, look, u1 minus u2 belongs to u and w2 minus w1 belongs to w. So that means u intersection w is equal to, so u1 minus u2 is equal to w2 minus w1 is 0. So u1 is equal to u2 and w1 is equal to w. That means that sum is unique. The sum, that means the sum is unique. Now, so that we can say, so that we can say v is equal to u plus w, that sum, and v is that sum of w implies u, v can be present at u plus w and u intersection w is, this is the sufficient condition. Again I explain this theorem one by one step. Let we assume that we have a direct sum of its surface. Then by definition v belongs to v, w belongs to w, u belongs to u. So v can be present as u plus w form. Now this is the first condition. Now for second condition we take that x belongs to u plus and intersection w. We take u intersection w is not 0. So there is a common element. Let we take x is a common element. X can be written as this form and this form. So x belongs to here, x belongs to u, and here u belongs to 0 belongs to u. So it concludes that a non-zero element of x, x belongs to v, can be written as a direct sum of subspaces element. So it may be intersection mean 0. Common element is 0. So this is the direct sum can be written as in this. Now sufficient condition that if V is equal to U plus W. V is equal to U plus W. And U intersection W is 0. So we will show that V is the direct sum of this U plus W. So we take by the direct sum, we take this is not unique. We know that the direct sum of the subspace is unique, but we here assume this is not unique. So V can be written by two elements. We can equal both elements by equalization both elements. We get U1 is equal to U2 and V1 W1 is equal to W. That means that means that means the sum is unique because U1 and U2 are equal and W1 and W2 are equal. So that we can say that V is equal to U. That sum of U and W. So the necessary and sufficient condition are fulfilled that V U plus W is the direct sum of V. We can if V U and plus W direct sum implies V is equal to U plus W and intersection of this is 0. This is a necessary and sufficient. So students, now we come to the cues on direct sum. Which is a condition for a subspace. W1 minus W2 belongs to in W A, A in F, W in W. Then AW is also in W. None or both. We know that if a subspace, then W1 minus W2 belongs to W and alpha X. Yeah, alpha W is also the part of scalar product is also part of W. So here the both conditions are required for a subspace. So D is the right option. What is true? Union of subspace again a subspace. Intersection of subspace again a subspace. Here see union of a subspace is not to be subspace because when it will be subspace then one subspace is subset of another. If W1 and W2 two subspace then W2 or W2 inside W1 then it make a subspace. So B option is right because intersection is always V subspace. Now, which is a true for subspace? Ax in W where x is a vector means A alpha W. Alpha W1 belongs to W. By in W, right? A scalar with vector multiplication is in W and alpha x plus beta y. Yeah, ax plus by in W. So three options are right. Alpha x belongs to W, beta y belongs to W, alpha x plus beta y belongs to W. So all option given option are right. A vector V is the direct sum of U and W if U minus W is 0, union of U and W are 0, intersection of U and W is 0 none. In previous theorem, we see that a function, a vector space V is the direct sum of U plus W if U plus W V it can be written as V is equal to U plus W and the intersection of them is 0. So option C is the right option. A vector V, a vector V if the direction V and W if U minus W is 0, 1 dot V in V, V1 plus V2 in V and D, V is equal to U plus W. So, this is again the statement of the theorem that necessary and sufficient condition of a direct sum H when V is equal to U plus W or U intersection W H U intersection W is 0. So, this is the all cues from the theorem. In linear algebra, abstract algebra, the theorem plays the most important part. So, student, all the theorem statements should be in your mind, in your and continuous watch and see the theorem statement. So, it will be helpful for your examination. And thank you very much. Thanks, students.